Now we still want to look at improper integration, but now we want to look at some cases where the integrand, the inside part, the thing that we're integrating, is not necessarily continuous over the interval given by the bounds of integration. Okay. So typically we would interpret something like this to mean that we want to integrate 1 over x on 0, 3, right? But of course, this function is not continuous on 0, 3, including 0. It is continuous on 0, 3, right? Not including 0. So we want to basically do the same thing we were doing with infinite bounds, where we want to exchange this bound for a limit. Okay. So we can go ahead and replace that bottom part with a limit here. But now when we take the limit, we want to be careful about exactly what we're doing, right? Because we want to take the limit as a goes to not necessarily 0, but because we're only looking at the right side of this, right, we would want to look at the limit as a approaches 0, specifically from the right side. Okay. So we'd want to look at this limit right here. So we would go ahead and do this like normal, just keeping in mind that we have to take this limit at the end here. So we get the natural log of, I'll just do it all at once, natural log of 3 minus the natural log of a. Okay. And now we want to take, the natural log of 3, we can just kind of leave that alone because that's just a number. But now we want to take the limit as a approaches 0 from the right of the natural log of a. Okay, so this one, I think it's clear if you remember how the graph of this looks, that this goes to negative infinity. So this is going to be 3 minus negative infinity, or 3 plus infinity, if you like. Either way, it diverges, right? It's not going to a finite number. So we say that this diverges. So I think this one is important to remember in particular, because sometimes you're just asked to like integrate something over some bounds, and if you just do it without really thinking about whether or not the function is continuous over that interval, you might just get a normal answer. And, it might actually be a divergent integral. Like, for example, I won't actually evaluate this one because we've used this 1 over x example a lot at this point. But, if I just asked you to integrate 1 over x from -2 to 2, and you just did it, well, I guess in this case, in this case you would get a normal answer, right? Because you're doing the natural log of the absolute value. So if you just did it, you would get the natural log of 2 minus the natural log of absolute value of -2. So you would essentially, you would get 0, right? But that's not necessarily actually what you would get. This is actually a divergent integral. So you do need to be careful about that. Okay. So we always want to, if we have a function which isn't necessarily continuous everywhere, we want to take a step back and we want to think, okay, this area that we're integrating over, is the function continuous over this entire area? Okay. So let's do some more examples here. So let's look at the integral from 0 to 9 of 1 over the square root of 9 minus x dx. Okay. So again, taking a step back here, we can see that this is not defined at 9, right? So this is defined everywhere else, but not at 9. So we do need to take a step back and put a limit in here. So namely, this function is defined from negative infinity to 9, not including 9. Okay. So we're going to, here we're looking at the left side. So we're going to be taking the limit as x approaches 9 from the left, or not x, but rather the bound, right? So we'll call it b. So we're going from 0 to b of 1 over 9 minus x. Okay. So to actually do the integral here, we can just do a simple substitution. So u being equal to 9 minus x here, this will imply that du is equal to negative dx, or that negative du is equal to negative or equals positive dx. So we'll do the limit as b goes to 9 from the left of the integral from 0 to b of 1 over the square root of u, and we'll have that negative, so we'll bring that on the outside here. And we'll go ahead and put the bounds, we'll do the reverse substitution before we worry about the bounds in this case. Okay. So the integral of 1 over root u, remember that's u to the negative 1/2, so it's going to be u to the 1/2 over 1/2. So it's going to be altogether negative 2 u to the 1/2. So we'll just say square root of u. And we'll go ahead and put that back in. So I'll just erase that and put a 9 minus x here. And then we're going to evaluate this from x equals 0 to x equals b. Okay. So we have the limit as b approaches 9 from the left of negative 2 root 9 minus b minus negative 2. So we'll say plus 2 root 9 minus 0. Okay, so that's just going to be 3. So this whole thing is going to be 6 over here. And then we'll have the limit as b approaches 9 from the left of negative 2, 9 minus b. So we'll just go ahead and sub 9 in right here. And we'll get 9 minus 9. So this is 0. So this whole thing is 0. So we're just going to be left with 6. Okay, so let's do an example that's relevant to probability. So this isn't a discontinuity one. It's just kind of another case that I want to show. So back to the infinite bounds, basically. But I am going to ask some questions that are kind of like this. So I want to do one that's like this. But basically the idea is that you get some kind of function. So let's look at this one in particular. And it's going to be a piecewise function. So that's important as well. Let's say that we have f of x equals lambda e to the negative lambda x when x is greater than or equal to 0. And we have 0 when x is less than 0. So again, in order for something to be a probability distribution, the integral of the entire thing needs to be 1. So the integral over the entire area where the function is defined. Sorry, there should be an equals here. So this is what's known as, this one in particular is known as the exponential distribution. Okay, so the exponential. And it's typically used to model the time between events of particular processes. So we want to show that the integral from negative infinity to infinity of f of x dx is equal to 1. Okay. Otherwise, it can't be a probability distribution. Notice that we're not saying what lambda is. Lambda is any positive number. Okay, so it's important that it's a positive number, but it's not important what number it is. So we can just work in terms of lambda. So we'll break this up into pieces based on the piecewise function. We kind of saw this when we were looking at how to integrate absolute value functions. Okay, so negative infinity to 0. On that piece, it's only 0. Okay. Plus 0 to infinity of lambda e to the negative lambda x dx. Okay. Okay, so this part right here, the integral of 0, the antiderivative is going to be 0. So even if you take the bounds or whatever, and you take the limit, it's still going to be 0, right? So this part's just going to be 0. So we don't really need to worry about that part. So we'll say 0 plus, and then this part, we do need to worry about a little bit more. Namely, notice that it does have the equal to part in there. So we don't have to worry about taking the limit as it goes to 0 from the right or anything like that. But we do have the infinite bound in there, right? So we need to do the limit as b goes to infinity of the integral of 0 to b of lambda e to the negative lambda x. Okay. So now we'll go ahead and evaluate this integral. It's a fairly easy integral, right? You can do a substitution here, but if you remember the rule that we had for integrals of this form that we wrote down in the integration by parts video, then you'll remember that this is equal to negative 1 over lambda times lambda e to the negative lambda x. So these will cancel, and we're going from x equals 0 to x equals b. Okay. So we'll have limit of b as b goes to infinity of negative e to the negative lambda 0 times 0 plus, because we'll have minus and negative, e to the negative lambda b. Okay, so it doesn't matter what lambda is. This is going to be 0, so we're going to have e to the 0, which is 1. Okay, so ultimately we're going to have the limit as b goes to infinity of e to the negative lambda b minus 1. Okay. Actually, I totally did my bounds backwards, didn't I? Yeah, this one should have been b, and this one should have been 0. Whoops. And that's, of course, going to be important here. Okay. So, it'll be the limit of negative e to the negative lambda b plus 1. Okay, so we can see where the 1's coming from. So we're hoping that this part goes to 0. Okay, so of course it does, because if we take the limit as b goes to infinity, this is going to be e to the negative infinity, which is like 1 over e to the infinity, right? So that's going to be 0. So this is going to 0. And we will indeed be left with just 1. So that means that no matter what lambda is, assuming it's a positive number, this is going to be equal to 1. And we can actually see right here why it needs to be a positive number. If lambda is a negative number, then negative lambda is a positive number. So then this is e to the positive infinity b, right? E to the positive infinity. So this becomes infinity and it no longer becomes 1. So it actually is very important that lambda is greater than 0, or else this wouldn't be a probability distribution function. It actually wouldn't be a convergent integral at all.